All right, next we're going to explore the power rule, and I try in the videos to try to kind of keep it brief and try to work on skills more than concepts, and of course both are going to come through. But this is one that I wanted to uh, just kind of show you how some of these things are derived and show you how the power rule is derived in particular. I think it's pretty interesting, and definitely always let me know if you want to know the whys behind some of the hows. In class, and that's one of the things I like about the flipped classroom is we can go into those some of those conversations maybe in breakout rooms or even individually while other students are working, so that students that because in the past I've had students that are like, Mr. Glory, don't tell me the why, I just want to know the how. The why kind of confuses me, and anyway, so that's always a tough balance because I'm very interested in the whys a lot of times, and as a student that's how I was, wanted to know the whys. So if that's you, then definitely feel free to ask me more about this, and we can go into it in more depth, or any questions or concepts that you have, or that concepts you have questions about, or if you want to know more in depth, how they're derived or things like that. Just let me know, and those are conversations I'm always happy to have. So anyway, so Pascal's triangle is something you may or may not have seen before, but it's basically a pattern where we start with this one on top, and then we put a one here and a one here, and then the subsequent rows and columns are just you just get by starting with one, and then you add the two on either side of it to get the middle. So 1 plus 1 is 2, so that's how I get that 2, and then I end with the 1. So then here I start with the 1, add these two together, 1 plus 2 is 3, 2 plus 1 is 3, and then we always end with a 1 here, okay? Or you can think of it as like 1 plus 0 there, right? And so then, continue down. 1 plus 3 is 4, 3 plus 3 is 6, and so forth and so on, right? So if we get 4 there. And so we can keep going with this, right? The next one would be 1, and then this will be 1 plus 5 is 6. Let me space out that 1 a little bit more. So then we get 6. 5 plus 10 is 15. 10 plus 10 is 20. 5 plus 10 plus 5 is 15. 5 plus 1 is 6, and then we get a 1 at the end. So we can see there's a lot of symmetry in that, right? And we can keep going with that forever. But how that relates with what we're doing now is we've done some binomial expansions, and we've talked about this to some extent. But this is the one we've done a lot, right? Like a lot of times we've had to square x plus h, and we always end up with this, right? So hopefully that's something that is very familiar to you at this point, and hopefully the formula makes sense and you can use it, and it's something that is almost second nature now. So we did this the other day on one of the homework assignments when we were trying to find the derivative of x cubed, and I forget if we were trying to find the slope of the tangent line or instantaneous rate of change. I think it was the slope of a tangent line. But remember, what we did is we got this, and then we multiplied by another x plus h. And if you remember, we got this, okay? And if you notice, like these are actually these. If you look at these coefficients, these are actually values of Pascal's triangle, right? Like here we have, if we have x plus h to the 0 power, anything to 0 power is 1. Anything to the first power is itself. And so notice these coefficients are 1 and 1, right? And then we have 1, 2, 1, right? And then we have 1, 3, 3, 1. And so notice how that's this. So if we multiplied by another x plus h, if we multiplied this by x plus h, what we would get, as you might imagine by the pattern, is 1x to the 4th plus, and then we'd get 4 x cubed h, and then we get 6 x squared h squared, then we get 4 again, x h cubed, and then we would get a 1 at the end with the h to the 4th. Okay, so notice how the x variables decrease, 3, 2, 1, 4, 3, 2, 1, and then no x right here, right? And then the h's increase, right? So we go from no h to h to the 1st, h squared, h cubed, h to the 4th. All right. So that's how, and this is somewhat of a side topic, but it's called binomial expansion. And every so often you'll see this on a standardized test where they'll put something like this, like x plus a or something to the fifth power. And so instead of trying to expand that by multiplying over and over again and foiling and superfoiling and going over that, if you remember Pascal's triangle, you can just go out to the fifth iteration, or really it's the sixth iteration if you include the first number there, but go out to where you have a 5 here, and that's where the fifth power pattern is. Okay. And so anyway, so that's a way to do that. And so now, the reason I wanted to show you this is because if we think about our derivative formula, we notice there's a pattern where a lot of stuff ends up canceling out, right? So if I have the limit as h approaches 0 of let's see, of f of x plus h minus f of x all over h, right? And then if f of x plus h is one of these values to some power, right? Like if we have a power or x value to some power, then it's going to be x plus h to that power, right? So like if we have a squared here, then this is going to be x squared right here, right? If we have this as our function, then this is going to be x plus h, or f of x plus h, and this is going to be f of x, right? And so we know what's going to happen is we're going to end up with this right here, 1x squared plus 2xh plus h squared, and then we're going to have minus x squared. And we keep noticing this over and over again where those x squareds cancel out, right? And then what happens from there is we can cancel out the h's, right? Like we can factor out a h, or we can cancel out one h from each of these terms. Okay. And then we end up with the limit plugging 0 in for h, right? And so this one ends up going away to 0. So all we have left is this term right here, right? And you may have noticed that pattern over and over again. So we end up with just 2x. All right. Now, if I do the limit as h approaches 0 of x cubed, then I'm going to get this situation going on. And what I'll have is I'll have x cubed, and I'm using this one here, plus 3x squared h plus 3x h squared plus h cubed minus x cubed, right, all over h. And so once again, the x cubes will cancel out. Then we can reduce the h's, right? One of these, so 2 are left. One of these goes away, so 1's left. This one goes away. And then what happens once again is we're going to plug 0 in for h, right? Because now we can directly evaluate. So this turns to 0, this turns to 0. Wherever there's still a h, it's going to turn to 0. So the only thing left that doesn't have a h is always that first term, right? That, or the second term, I should say, right? Because the first term that's left, but the second term after x cubed. And so if you think about Pascal's triangle, what you notice is, like, we're always going to have that term as our resulting value, right? And then the exponent, or the variable that you'll have with that, is always x to 1 less power than what you started with, right? So this is like x to the first, x squared, x cubed, right, and so forth and so on. So we end up with this number as our coefficient, and we end up with 1 less than that number as our exponent. Okay, and that works just by the nature of when you expand binomials, right? And this is the pattern that it happens to have naturally. And so it ends up being where all you have to do with the power rule is just, if you start out with f of x to the nth power, you can just multiply by n. You can put the n in front, and then just subtract 1 from n. Okay? So you multiply by n in the front, and then you just subtract 1 from it, and that's the power rule. And it happens because of what we just talked about with binomial expansion, and then the way our limit rule works, where everything cancels out, or where the first term cancels out, right? Because it's f of x. And then everything after the second term cancels out because they all have an h attached to it after you divide by h, or reduce by h. And then so the only thing left is that second term, and that second term is always whatever the exponent is as a coefficient, and then with x to the 1 minus whatever that exponent was to begin with, right? Okay, so that's the power rule. And that's kind of an informal proof, like an intuitive way to understand why the power rule works. This is saying the same exact thing, right? It's just using our ddx, our Leibniz notation, instead of our prime or Lagrange notation. So it means the same thing, right? ddx of x to the n is what happens is we multiply by n in front, and then we just take 1 away from that exponent, and that's our final answer.